So for a horizontal mass spring system, if we assume our surface to be frictionless, what kinds of energy are going on there? Well, we know we have spring potential energy, and we also have kinetic energy. For a vertical mass spring system, as it's moving up and down, we have gravitational potential energy as well as spring potential energy and kinetic energy. Now, remember from our discussions of energy last semester that only a difference in potential energy has physical significance. So for a vertical mass spring system, if we consider the energy when it's at the equilibrium of the mass spring system versus the energy when it's at some other point, let's think about what that is. And especially versus, so this is, say this spring is unstretched entirely, and then the energy at some random point. So from unstretched to stretched, I'm going to call this value y eq for equilibrium, and then I will call this value y. It's just the vertical position at any given time. So let us consider the difference in potential energy from equilibrium to this point. I'll call that point 1. Well, let's see. So at equilibrium, let's take this point first. At this point, what is our gravitational potential energy? If we set our zeros for everything right here, then we have our gravitational potential energy is minus mg y. Our spring potential energy is 1/2 k y squared. So that is our potential energy at point 1. Difference, you subtract. What is our potential energy at this equilibrium position? Well, that's just minus mg y equilibrium plus 1/2 k y equilibrium squared. Now that doesn't seem very helpful yet, but what do we know at the equilibrium position of the mass spring system? At this point, we know, because it's equilibrium, that force is 0. What forces are acting? Well, there's a spring force upward, there's a gravitational force downward. So at that point, we know, well, that's not vertical, so it's not x, it's y. Ky eq is equal to mg. So if I go ahead and make that substitution down here for the mg's in both of these, then what do we have now? We have minus ky eq y plus 1/2 k y squared plus, distributing the negative gives us plus k y eq squared plus 1/2 k y eq. Oh, sorry, distributed the negative, that would not be plus, that would be minus 1/2 k y eq squared. These are like terms, so we can add them together, which gives us 1/2 k y squared minus k y eq times y plus 1/2, 1 minus 1/2 k y eq squared. Right. Now, this should look familiar. This is the pattern for a binomial squared. This is the same thing as 1/2 k times y minus y eq squared. So, and what is this? Well, y minus y eq, or the other way around, it doesn't matter because it's squared, is just the difference in height between the equilibrium position of the mass spring system and whatever position it happens to be at. So this is 1/2 k delta y squared. So what's the point of all that? Well, the point of all that is that then, since we just get this 1/2 k delta y squared, if we have things in reference to the equilibrium position of the system, then we can treat the equilibrium of the mass spring system as the zero of potential energy and ignore gravitational potential energy. It's still there because, we started with that, but we can just treat it as though the zero of the spring is at the mass spring equilibrium position, and then only consider gravitational potential energy. Now there's a warning here, because you can only do this if you have distances and so forth relative to the equilibrium position of the mass spring system. If you have the equilibrium length of just the spring, and that's what you have distances relative to, then you need to consider both spring and gravitational potential energy. Okay. Just a reminder, potential energy of the spring, I didn't leave enough space there. Potential energy of the spring is 1/2 kx squared. Kinetic energy is kinetic energy, as always, 1/2 mv squared. So where is potential energy at a maximum? Well, 1/2 kx squared. Potential energy is max at maximum displacement from the equilibrium position of the system. Where's potential energy a minimum? Well, that's when x is 0. So potential energy is a minimum at the minimum, or at, I shouldn't say not just the minimum, at 0 displacement from equilibrium, or at the 0 of equilibrium. Where is kinetic energy a maximum? Well, maybe I should jump down here first. What forces provide the restorative force for mass spring and pendulum systems? Well, for mass spring, it's the spring force. For pendulum, it's the gravitational force. And both of these are conservative forces. So what principle applies? Well, conservative forces conserve mechanical energy. So mechanical energy is conserved. So going back up to this question, where is kinetic energy a maximum? Well, where kinetic energy is a maximum, where potential energy is a minimum, so that's at 0 displacement. Where is kinetic energy a minimum? In fact, it is 0. Kinetic energy is 0 at maximum displacement. And we already know that. We talked about the velocity being 0 at maximum displacement. And if the velocity is 0, then kinetic energy is 0. So we can also say, and I didn't put a spot to state this specifically, but we can also say our total mechanical energy is equal to the maximum potential energy, which is 1/2 kx squared at maximum displacement. The maximum displacement is amplitude squared, and that's the same thing as the maximum kinetic energy, which is 1/2 mv max squared, and the maximum velocity happens at equilibrium, the equilibrium position of the spring. We already did stuff with this actually last semester. Now, let's think about this too. So we know potential energy is 1/2 kx squared. Well, what is x? Well, it's 1/2 k, and we know x is amplitude cosine omega t plus phi squared. So our potential energy is 1/2 ka squared cosine squared omega t plus phi. What is kinetic energy? 1/2 mv squared. Well, we know that's 1/2 k, and velocity is minus a omega sine omega t plus phi squared, which is, I'm sorry, I threw in a k there randomly, 1/2 m times that, yeah. So that's 1/2 m a squared omega squared sine squared omega t plus phi. And you might not recognize this off the bat, but m omega squared, what is that? Well, we know for a spring, omega is root k over m, so omega squared is just k over m times m gives us just k. Therefore, our kinetic energy is 1/2 k a squared sine squared omega t plus phi. So then our mechanical energy, which is u plus k, what do we have? We have 1/2 ka squared cosine squared plus 1/2 ka squared sine squared. And you may remember from pre-calc, cosine squared plus sine squared is just 1. So our total mechanical energy equals 1/2 ka squared, which agrees with what I set up here. If I was to make a graph of these, and I'm just going to make a very rough sketch, because we want to get an idea of what these things look like. Well, our mechanical energy is a constant. So this is my, I write ME in all my other classes, but your book says EMAX, so I want to stick with that. Our mechanical energy is a constant value. So if we graph energy versus time, mechanical energy is just this constant value. Potential energy has a maximum value that is the same, but it's a cosine squared. It starts at a max, and so potential energy is going to oscillate back and forth. The cosine squared looks basically like cosine, but has a minimum at 0, and it'll go on and on and on. Meanwhile, sine is kind of the same deal, but the sine function starts at 0, and I guess this graph is assuming, for the graph, we're assuming phi is 0. I mean, if you just shift the y-axis over to somewhere, then you can see what it would look like if phi was not 0. Anyway, sine of 0 is 0, so we're starting at a minimum there, and potential, or this is the kinetic energy that's going to have a maximum wherever potential energy has a minimum, and vice versa. And though I've drawn this kind of like it looks like this is kind of halfway, but it's not actually halfway. Right here is where sine omega t equals cosine omega t, and that happens to be where omega t equals pi over 2. And the sine of pi over 2 is root 2 over 2. Oh, it is half, because you square that and you get half. I wasn't okay. I guess it is halfway for where the sine squared and the cosine squared meet. Okay. All right.